Okay everyone, so hopefully this video will go smoother than my last my first stoichiometry video. I'm at home today, so hoping that you or I won't be interrupted. So we're going to talk about chemical equations today. We did a little bit of this in class to kind of get an idea of what you knew, and I was pretty impressed by how well everybody seemed to know that, how to balance equations and also, how to do stoichiometry problems. But I'm just going to give you the notes on them. You can watch, as much of this as you want. At the end of the video, though, I would recommend that you, fast forward to where I start doing limiting reagent problems and try some of those on your own. I'll put a few up at the end of the video for you to try, and then we can go over them in class also. So when we talk about chemical equations, there are some key terms that you need to know. The first one being the coefficient. So the coefficient is the number in front of a substance. So if we have a chemical equation like hydrogen reacting with oxygen forming water, and I balance this, which we'll do together in a second. On the next slide we'll do another balancing one, but if I balance it and I put a 2 in front of the hydrogen, what that's kind of telling me is that I have 2 moles of hydrogen, or I have 2 molecules of hydrogen. Almost always we're dealing with moles, so 2 moles of hydrogen reacts with 1 mole of oxygen, and then it forms 2 moles of water. So the number in front of the substance, that tells you either the moles or it tells you the number of molecules. Now the subscript, that tells you, or that's the small number. So H2, for example, and that tells you the number of atoms, or if you want to say moles of atoms, per molecule, or moles of molecules. So in this case, if I were to look at the H, I would have H2, and that H2 would tell me that I have 2 hydrogen atoms. If I were to have the 2H2, I could multiply the large 2, the coefficient, by the subscript, and I could get 4. And that would give me 4 atoms total. Then you have the reactants and the products. And so the reactants, that is on the left side of the arrow. And it's really what you're starting with, the starting substances. And then you have the products is what you produce. It's on the right side of the arrow. And it's what you end with. So now if we look at an equation here, we want to be able to balance it. That's always the first step. You always need to check that the equation's balanced. And what we'll get into a little bit later is you need to balance based on mass, where we're going to use coefficients. But also, you need to balance based on charge. So you got to be careful with that. And I look at these and I see that they're all neutral, either atoms or molecules, and so I don't need to worry about the charge. But sometimes you do, and those are, a little bit tricky, and you have to be on your, on your game in order to get them. So when I look at this, I have my aluminum, and I could set up a little chart since this is the first one that we're doing. We'll do aluminum, hydrogen, and chlorine. Those are the atoms that are on both sides. And I look at my aluminum and I have 1 and 1. And I look at my hydrogen and I have 1 and I have 2. Well, why do I have 2 hydrogens? I look at the subscript and I look at the coefficient and I see that there is 1 times 2. And so really, when I want to find the number of atoms, which is what I'm trying to equal, then I multiply the coefficient by the subscript. And so those don't match up. We have an unbalanced equation. And when we do the chlorines, we have 1 chlorine on the left, and then 1 times 3 is 3 chlorines on the right. So it doesn't really matter where you start. I'd probably start with the chlorines, but I could do the hydrogens. Doesn't really matter. So if we start with the chlorines, we're going to need, and we can zoom in here, we're going to need 3 chlorines. So we can only put numbers in front. I put a 3 in front. My chlorines are balanced. So I can change this to a 3. My hydrogens, now I have 3 and 2, and that doesn't work. And so a lot of times I'll do a least common multiple. So I know the least common multiple between 3 and 2 is 6. And so then I'll try and get 6 hydrogens. So doing that, if we put a 6 here, that now changed the number of hydrogens to 6. And I need 6 on the right side. So think about what number I could put on the right there. If you put a 3, 3 times 2 is 6. And so now, when I go and inspect this, 1Al, 1Al, 6H's, 6H's, 6 chlorines. Oh, and I have to balance the chlorines. That's not balanced now. So now I need to put a 2 here. 2 times 3 is 6. But that changed my ALs. Makes it a 2. I need a 2 here. Look at how many iterations I went through. If we look at all the crossouts on the screen, the hydrogen required trial and error twice. The chlorine required trial and error twice. This is sometimes, a journey. Like you're going down this road. It doesn't always work the first time. Putting a 3 in front of the HCl didn't work for me. I had to erase that and I had to put another number. And that's okay. So another thing that you'll do, and we can get to a more complicated one, is, if you had something like, sodium sulfate, and you added that to something like barium chloride, and you formed a precipitate. And that would give you NaCl. So a lot of people, they'll break the S and the O apart, and I think that that's a poor move. I think that you should look at it like this. You have sodium, you have sulfate, you have barium, and you have chlorine. Now you don't have to create a table like this. A lot of you are doing this by inspection. 2 NAs, 2 NAs, 2 CLs, 2 CLs, 1 SO4, 1 SO4, 1 BA, 1 BA. And you're already balanced. One last one, which I'd like you to try on your own, and we're going to come back to this one at the end when we do a limiting reagent problem, is why don't you try something like, C4H10 plus oxygen yields CO2 and H2O. So we'll write this again. We'll use this one for a limiting reagent problem later on. Let's see if you balance it correctly. Then we can talk tomorrow about tips on how to balance. So, now that we have a balanced equation, we need to do some stoichiometry with it. That's the fun part. So when I want to go ahead and do the stoichiometry with this, here's my typical type of question. This one's, a medium one. There's no limiting reagent in this. It says if you have 200 grams of aluminum, how many grams of hydrogen will you form? So first, let's make sure it's balanced. Now this one I know is balanced. We did it in the previous problem. So now I have to decide what substances I'm going to compare. So I look back at the problem and I see that in fact they want me to compare aluminum and they want me to compare that to hydrogen. And so now I sort of make like a little list of things I know. You could do a table, but you don't really have to. So I know that I have 200 grams of aluminum. And I know that I want to find how many grams of hydrogen. So those are the two things that I'm going to compare to one another to try and figure out, what it is that I need to do here. So I know I need to find the grams of hydrogen, and I know that I have the grams of aluminum. So now let's see how we're going to set this up on the next slide. So I'm starting with my 200 grams of aluminum. So the first thing that I decide to do is I'm going to take the grams and I'm going to make it into moles. So I divide by the gram formula mass and I get the moles of aluminum. The second thing that I'm going to do is have a mole ratio. So I'm going to take these 7.4 grams of aluminum and I'm going to multiply them by the ratio of hydrogen to aluminum, the two substances that I want to compare. And I would end up with 11.2 moles of hydrogen. So my second step is always to do a mole ratio. And then my third step is to go back to the amount of grams. So I take the moles that I have of hydrogen, and now I multiply it by its gram formula mass, which is 2 grams per mole. And then that will bring me back to my amount of grams of hydrogen, and this would be H2 here. And so step 3 is to bring it back to whatever unit you want until you get your answer. So what did we do here? We found out what was given. We converted the quantity, in this case was grams, we converted that to moles. We used the equation's mole ratio, and then we converted the moles of the second substance back to grams. 3 steps. We did a quantity, and we changed that to moles. We did a mole ratio, and then we changed the moles back to whatever quantity we wanted. So how does this look in another problem? Well, we can use this graphical interface to figure it out. This is the general graphical interface that we would use when we're doing this type of question. Step 1, use a mole conversion to go from quantity A to moles of A. Step 2, use a mole ratio. And step 3, change the moles back to the quantity of the new substance. So let's look at another problem here. So we want to know how much water is produced. So I make sure that the equation's balanced. 1 glucose plus 6 oxygens yields 6 carbon dioxides, 6 waters. And so we're starting with 5 grams of glucose. So our 5 grams of glucose, we're starting with this substance. And they're asking us how many grams of water. So we're going to this substance. Honestly, I could ignore the other ones. I don't care about the oxygen or the CO2. So now the 5 grams of glucose. So I need to change this to moles. 5 grams times 1 mole for every 180 grams. So when I do that, let's see what we get here. So we do our 5 divided by 180, and we get 0.0278 moles of glucose. Now we do our mole ratio. Well, we have the 0.0278 moles of the glucose times 6 waters for every 1 glucose. So we times our answer by 6, and we get 0.166, or 167, moles of water. And then we change that to grams of water. 0.167 moles times 18 grams for every 1 mole. Step 1 was to change grams to moles. Step 2, use a mole ratio. Step 3, change it back to grams. If we change that back to grams, we get 3.00 grams. Three steps. Let's try another one. This one I want you to try on your own. Tomorrow in class we'll go over it. Now, if you don't like all these arrows, just do it on the bottom here in one step. You don't need to follow my graphical interface. But I want to go over this one tomorrow, okay? That'll be Monday. Now let's look at like a limiting reagent problem. So a limiting reagent problem is more challenging because what it means is that you're going to run out of one of your reactants. They call them reagents because in the lab they're working with chemicals. They're called reagents. That's why they use that term. So, let's use like a real life example. Let's say that you are going to try and make sandwiches, cheese sandwiches, and you're using cheese and you're using bread. And so, I would have, for this, to make a sandwich, 2 slices of bread and 1 slice of cheese. It would be 2 slices of bread plus 1 slice of cheese would give me a sandwich. My sandwich would look like this. In this case, B stands for bread, C stands for cheese, not boron and carbon. So now I go ahead and I say, well, how many sandwiches can I make? A lot of you already look at this and you're like, you can make 5 sandwiches. You just know it. But what would the math look like if I was doing this? Well, if I was going to have my 10 slices of cheese, No, I'm sorry. You couldn't make. I mixed it up. So you can look at this and you can say, 10 slices of cheese versus 7 slices of bread. You'd say I can make 3.5 sandwiches. So let's see what happens here. How can we make 7? How can we figure that out? Well, if I take my 7 slices of bread, how many sandwiches could I make? Well, for every one sandwich, they are using 2 slices of bread. So this tells me that I can make 3.5 sandwiches. Well, if I have my 10 slices of cheese and I make 1 sandwich for every 1 slice of cheese, I can make up to 10 sandwiches. So I have 2 answers here, but only one of them is correct. What's going to be the correct answer here? Well, if you said the 3.5 sandwiches, you're right. You're never going to get to 10 sandwiches. You're going to run out of bread because it takes 2 pieces of bread to make every sandwich. Once you run out of the bread, you're done. This is the maximum number of sandwiches that you can make. This is the correct answer. And a good trick for this when you're doing a limiting reagent problem is you can always just go with the smaller of the 2 answers. So the smaller is correct. What does that look like, if I was doing this with a real actual problem? Well, let's try something like this. We're going to try and make ammonia. And we're going to try and form this from 3 moles of nitrogen and 6 moles of hydrogen. So now, notice, with these limiting reactant problems, they give you both reactants. So let's go through what we did with the cheese and bread. Let's take the first reactant, the ammonia, and let's multiply it by the mole ratio, and we get an answer of 6 moles of ammonia. And then let's do the same thing with hydrogen. Hydrogen, the ratio is 2 to 3. So we times it by 2, divided by 3, we get 4. Only one of these can be correct. Just like we ran out of bread, here we're going to run out of hydrogen. Now also, honestly, when I look at this, I picked this problem because what I wanted to do was I wanted to actually have a situation where I gave you one of the reactants that was more. Notice how I gave you 6 moles of hydrogen? A lot of people would look at those moles of hydrogen and just say, hey, it's going to be the excess one because there's more hydrogen. Just because there's more hydrogen doesn't mean that it's excess. We see that in this example. And that's because it depends on the ratio. Yes, there's 6 moles of hydrogen, but also the ratio is 2 to 3. And so I have 4 moles of ammonia that's made. And those 4 moles of ammonia are the correct answer. The 6 moles of ammonia will never be made. This N2 is in excess. Now, we're going to do a problem where we actually figure out how much is left over. And I want you to keep that on the side, and maybe come to class we can discuss that. One of the things that we need to do and be able to look at is, well, how much excess reactant remains. So we'll do a problem like that, and we'll even use this example to try and go through this and see. Maybe you'll have an answer, but we also need a method, and you'll see that on the next slide, or 2 slides, how that works. So here's another problem with limiting reagent. This one's a little bit more complicated, the numbers aren't as pretty, but we go through and we, try and solve for it. Do the same thing, we convert the mass to moles. So first we have the barium nitrate. We change that to moles by dividing by the gram formula mass. We get the moles of barium nitrate. We have the mass of the sodium phosphate. We change that to moles of sodium phosphate. So let's figure out which one's going to give us the least product. They asked us how many grams of barium phosphate are formed. So let's find out how much barium phosphate's formed. So the first one I do is my barium nitrate. So I have my moles of barium nitrate. I use the ratio, it's 1 to 3. I find out that I make this much, and we'll do a different color here. I find out that I make this much of the barium phosphate when I use the barium nitrate. Now let's do the sodium phosphate. The sodium phosphate, we take the moles, and we find out, well, how much barium phosphate do we make? In this case, the ratio is 1 to 2. And so we figure out that we have this many moles of barium phosphate when we use the sodium phosphate. So now we say, well, which one's less? Well, since there's less phosphate made using the barium nitrate's limiting. So let's take those moles that we formed right here. Let's convert it back to grams, times it by the gram formula mass, and we get the grams of barium phosphate that forms. So in this situation, we're always doing the same thing. We're just doing a stoichiometry problem twice. Now, the last thing that I'm going to do with you in this video is looking at what happens when you have limiting reagents and they want to know how much is left over of each reactant. So let's look at our problem above here and apply it to that. So just to go back to this, if we have our barium, our two reactants, our barium nitrate and our sodium phosphate, we already know that this one is our limiting reagent and this one is our excess. We know that because we figured out how much product formed. So now, to find out how much is left over, we do a ratio between the reactants, between these two reactants. And the first thing that we need to do in step 1 is we need to find out how much sodium phosphate, how much excess actually reacted. And we do that by this general formula. We take the limiting reactant moles and we times it by the ratio of excess to limiting from the chemical equation. So look at how we do that. We take the moles of the limiting, the 0.0245 moles. We multiply it by the ratio of excess to limiting. And this tells us how many moles of excess that were used. Now once we know the excess moles used, then we can subtract that from how much we had. And you should get a positive number. So this is how much excess we started with, and then we subtract it from the excess that we used. That will give us the excess left over, and then we can times it by the gram formula mass of that reactant, and we can get the grams left over. If you subtract them and you get a negative number, then you know you did something wrong. So try this for the ammonia problem, and we'll do that in class tomorrow. And then let's try this for one last problem, a problem where we're going to take the butane, and we'll insert a slide here, the problem where we're going to take the butane and we're going to react it with oxygen. So hopefully you balance this equation correctly. C4H10 plus O2 yields CO2 plus H2O. So hopefully you balanced it correctly. So there should be 2 of these. There would be 8 of these. There would be 10 of these. And then we would have 16 and 10 is 26. So that would be 13 oxygens. We could talk about how to balance this, but let's say I give you a problem where I gave you 80 grams of C4H10, and I asked you to react that with 250 grams of oxygen. And I asked you 2 questions. One, how many liters of CO2 form at STP? And then I also ask you the second question, how much or how many grams of each reactant remain. So these are my two questions for you. We'll go over them tomorrow. We'll talk more about limiting reagents and keep going on with stoichiometry. Hopefully Alex and maybe Jared will come up with my theme song and my logo so that my videos can be complete. But for now, I hope this was helpful. Thanks.